I had no idea that ordinary things could be so loud.
Yeah, it's really going to make me rethink some of my iPod choices.
You like it loud?
There's only one way to rock.
It sounds funny when you say that.
Anyway, what do you know so far?
So far, I know that sound is vibration that gets picked up in my ears.
Good. Well, plenty of things vibrate, but you can't hear them all.
What do you mean?
Well, there are some things we can quantify about vibrations, and one of them is frequency.
I've heard of that before, but I don't know what that means.
Oh, I can show you. When we're talking about vibrations, we're actually talking about waves, and there are things we can specify about waves. The first is called the wavelength. It's the distance between two peaks on this wave. Another important one is called the frequency. It's the number of waves that go by in a certain amount of time. The last one we like to talk about is called the amplitude. That is the height of the wave. Scientists like to talk about frequencies and wavelengths, but musicians like to talk about pitch and volume. And pitch, that corresponds to frequency, and it looks a little like this. You see, a high pitch has a high frequency, and a low pitch has a low frequency. The loudness or volume is related to the amplitude, and the louder a sound, the larger the amplitude. I can show you that on this guitar. If I play a note here like this, first it's very loud and has a large amplitude, but over time it gets quieter. And the cool thing is that its pitch never changed.
I get all that. So it's all about vibration.
That's right, but now we're getting to the musical portion of things.
What do you mean?
Well, you know, instruments tend to vibrate at certain frequencies, some more so than others.
So is that what makes them sound so different?
Yes, and we'll get to that, but first I'd like to introduce you to the power of resonant frequency.
What is that?
A resonant frequency is a frequency that has the potential to set up a vibration with a very large amplitude.
That means a large vibration.
Yes, it's almost as if instruments were made to vibrate at certain frequencies.
Okay.
Every instrument, or actually everything, has its own natural frequency.
So everything that likes to vibrate or shake in its own way?
Yeah, with a very large amplitude.
How large?
Large enough to break something.
No way.
Way.
So what we're going to do today is explode a wine glass using resonance. But the first thing we need to figure out is what frequency the wine glass is vibrating at. To help illustrate the concept of resonance, I have 4 graduated cylinders here filled with blue water, and I also have a tuning fork to provide the vibration. Now, when something resonates, it's when you force it to vibrate at the frequency that it wants to vibrate at. And only one of these 4 graduated cylinders is going to match up with my tuning fork. So let's try each one. Not that one. This is the one where you can hear the sound of the tuning fork inside the graduated cylinder. If I try any of the other ones, I don't hear anything. There's only one cylinder that resonates with my tuning fork because its natural frequency, its resonant frequency, lines up with the frequency of my tuning fork, which is why I can hear it inside the cylinder. Here I have a PA speaker with a sheet of cardboard over the front with a small hole cut in it. And the reason for this hole is that it keeps my sound waves nice and focused on the glass. So all the energy from the speaker can go into resonating my glass. And to show that the glass is actually vibrating, I have a straw that I'm going to put in it. If the glass is vibrating, that straw is going to start dancing. And now that we've seen the glass jiggle from resonance, when I force it to vibrate at its resonant frequency, now it's time to break it. And for that, I'm going to use my safety glasses. If I play my sound loud enough, that wine glass should resonate itself apart. Not only will a wine glass jiggle a straw in it, but it's also resonating strongly enough to shake a pencil. So as you can see, the glass was shaking, and it was shaking so strongly that it finally fell apart. If you look carefully, you'll notice that the glass is a lot thicker than you would think in a wine glass. It's interesting, isn't it? So when you force something to vibrate at the frequency that it prefers to vibrate at, you get something called resonance. And the vibrations just keep getting bigger and bigger. Thank you.
That was so cool. I mean, I heard it could happen, but I didn't know it could actually happen.
Yeah, and what's also cool is that it showed us that things can vibrate at more than one frequency at the same time.
Really?
Yeah, watch this. I'm going to play it to pure tone. And now I'm going to play a same note musical tone.
They sound similar, but not the same. Why are they so different?
The instrument has its own natural resonant frequency. Because of its shape and its composition, there are also many other frequencies present. We call those overtones.
Cool.
Overtones are some multiple of the resonant frequency. And collectively, when you put them all together, that gets called timbre.
And that works because the wave adds up.
That's right. All of the overtones are added up with the natural resonant frequency, and you get the sound that you're used to.
That actually makes sense.
Good. So now let's see it in flames.
Oh, what is this? This looks really cool.
This is a Rubens tube, and I think we can get some answers on it. Hi.
Hi, Mike.
Good to see
Max.
you.
Hi.
Welcome to Northwestern University. This is our Department of Physics and Astronomy in our main lecture hall.
It's beautiful.
Oh, neat.
And I can't help but notice you've got a lot of little candles here.
Yes, indeed.
This is beautiful. What is this?
This is a Rubens tube.
Rubens tube, okay.
And what we have is we have a natural gas source over there feeding natural gas into this tube.
Mm-hmm.
The gas passes through holes in the top of the tube, and when it mixes with air, it causes a flame.
A lot of little, like a lot of little candles.
You cook a lot of ribs on here.
A lot of hot dogs, too. Now, it turns out that the tube is all at the same pressure, so
Okay.
all the flames are at the same height.
Yes, they are.
And what we got on the end here is a speaker
Okay.
that we're going to send sound down the pipe,
Uh-huh.
and then it's going to reflect off back the other end and come back again. And we're going to have these sound waves and passing through each other in the pipe. And as they do, they will interfere and cause, where the amplitudes are in phase,
Mm-hmm.
they will cause a higher pressure.
Okay.
And when the amplitudes are opposite, they'll cause a lower pressure. And a variation of pressure will appear as a difference in height of the flames.
So I
along the
think we're
length
going
of
to
the
see
tube.
these flames change when we start to turn on the sound. So is that going to cause the gas in there to start to vibrate a little bit?
That's right.
Okay.
Well,
So let's see what this looks like. then.
okay, so I'm going to pick up the amplitude, and I got a particular frequency now.
Oh, you can hear a sound.
Yep.
Yeah.
Oh, look at that. Wow.
See the peaks? So this is like when you see on a recording, like the waves.
Mm-hmm.
Mm-hmm.
It's the
So I
same.
see a peak here and a little trough, a peak and a trough. This is exactly what we'd expect to see.
Yep. So what we actually visibly see then
Mm-hmm.
is a wavelength of the sound that we're
Mhm.
producing right here.
So a wavelength would be sort of like from this trough to this trough, or this
Right.
peak to this peak.
Right.
So what happens if we change the frequency a little?
Well, if we change the frequency, that should change the wavelength,
Okay.
and
So
we'll have to
this
find
distance will change.
a frequency. I'm going to bring the frequency down
Okay.
and see if we can't make it vibrate at another frequency.
There we go.
So
So you lowered the frequency, right?
lowered the frequency.
So that means that the distance between these two waves should get a little bit longer.
Right.
I have a question. Now, this speaker is vibrating the gas that's inside here.
Correct.
So is that where the sound is coming from, or is it coming from the tube?
I think the speaker is, the sound is actually coming from all along the tube, yeah,
Mm-hmm.
because that sound is being broadcast through the entire length of the tube. So it's one large speaker.
That's really cool. Now, of course, we can't see the gas in there actually vibrating. So
That's
I wonder,
right.
do you have a way that we can visualize what it looks like when the gas inside there is vibrating?
Yes, I have a little piece of equipment right over here.
Oh, okay.